Good afternoon, everyone. So I hope you can hear me. I hope you can also see the cover page of Ronitt's slide. So it's my immense pleasure to have with us today Ronitt Rubinfeld, who will be talking about local computation algorithms. But let me first say a few words about Ronitt. So Ronitt is a professor of electrical engineering and computer science at MIT, and also a professor of computer science at Tel Aviv University. She's renowned for her amazing research in computational complexity, randomized algorithms. Recently, she has been working a lot in property testing, sublinear algorithms, some parallel algorithms, distributed algorithms, in general studying foundations for measuring the performance of algorithms that analyze data without looking at all of it. Ronitt was an invited speaker at the International Congress of Mathematicians in 2006. She is an ACM fellow, and last year she was elected to American Academy of Arts and Sciences. So before I will let her start the talk, let me just also remind you about the rules. So if any of you have any questions, please put them in the chat or Q&A, and I will just read them. We'll interrupt Ronitt. Otherwise, let's just start. Ronitt, thank you.
All right, thank you. So I'm going to talk about local computation algorithms, and the setting is you have super large inputs, so big that you don't have time to read the whole input. And what can you do? And this is what I've been working on for, I don't know, maybe 30 years. But recently, what I've been interested in is not just when the input is large, but what happens when the output is also large. So no longer are we interested in just testing a property, just saying a bit, yes or no. Is the graph bipartite? Is the graph not bipartite? Is the list of numbers sorted or not? Now we want actually an output. So I want to know not just like how big the vertex cover is, but what is the vertex cover, or so the output is large, too large to write, okay? But maybe you don't need to see the whole output. Maybe you just need to see pieces of the output. And when that's the case, do you need to compute the whole output? Well, maybe not, but furthermore, maybe just to compute a piece of the output, do you need to see all the input? So that's the questions we're going to try to answer. I'm going to give a survey in this type of work. So it's a partial survey. It's not comprehensive at all. I'm going to give some of the kind of old techniques that are from many years old, but I'm also going to move on to some newer things as the talk progresses. So that's what I want to talk about. I do want to say this model may sound familiar, even if you haven't seen this particular model before. It's similar in spirit to locally decodable codes. Here, the input would be an encoding of a very large message. So this is a really, really big input. The output of the decoding algorithm would be the original large message. By the way, I'm advancing slides, so if you don't see me advancing slides, please tell Artur. And also, if you don't see my cursor, tell Artur, because I need to know. So
I see your cursor, I see your slides.
Great. Now, every time I move my thing, everything's moving. Sorry, that's because I'm moving my mouse to move my cursor, and it's moving my slides by mistake. Sorry about that. Okay, so the output of the the output of the decoding algorithm is the original large message. Okay, both the encoding and the decoding are huge. We don't have time to deal with that. But maybe the user just needs to know what is the ith bit. Maybe the user just wants to do binary search on the original large message to figure out if their name is in the list of people included in this message. Okay, so can we do that? And in fact, there are these things. There are these locally decodable codes and locally list decodable codes, which allow you to make very few queries to the encoding in order to figure out what's the value of the ith bit. So this is the sort of thing we'd like to do, but now for other types of objects, such as graphs and other lists of numbers and so on. Okay, so let's take the example of maximal independent set. Here you have an input graph, and I'm going to assume its degree is at most delta. And I'd like to just to make sure we're on the same page, we're talking about maximal independent set, not maximum independent set. So this is something that can be done in polynomial time with the greedy algorithm. And your input is some huge graph. So that's your input. It's a huge graph. And now you want to know for a specific node U, is U in the maximal independent set? Okay, so the output would be the maximal independent set, and we're making queries. We're asking, is U in the maximal independent set? Is V in the maximal independent set? And so on. And we'd like to support such queries without building up the whole maximal independent set and also without looking at the whole input. Okay, so the lazy greedy algorithm, here's a first crack at trying to answer that. When you get a query, is node U in the maximal independent set? What you can just do is be lazy, okay? If you can check, have the neighbors of U been put in the maximal independent set? And if you see that they haven't been touched yet, then put U into the maximal independent set. Okay, so if none of the neighbors have previously been put in, then it's safe to put U into the maximal independent set. This is just greedy, but you have to remember your decision. Okay, so what does this take? U needs to look at all its neighbors. We said that the degree was bounded by delta. So this is order delta time per query, but you do need a lot of space because you need to remember all your past decisions. Okay, so, all right, so notice that the answer, the maximal independent set we output, could vary depending on the query order. So furthermore, we have to remember all past choices. And a third thing, which might be useful in certain cases, and I'll talk about why in a minute, you can't allow simultaneous non-interacting copies of the algorithm because I need to know, like, if I don't interact with you, okay, so I'll give you the example right now. When do you need maximal independent set? When you are giving an exam to a very large class. Say we had a data structures exam, 300 people, they all come into the room at the last 5 minutes. We have a large course staff, but we were trying to make sure that there was enough room to seat everybody in this auditorium. And in order to do that, we had to help them sit down into not just a maximal independent set, but actually a good maximal independent set, because otherwise they always left 2 seats in between. So you need the people to sit down so that there is nobody sitting next to each other. But you also don't want that, we didn't want them to waste space. So we wanted them to sit every other seat, not every third seat, which is what they would have done on their own. So so basically we had this whole staff of TAs and me and a couple of other faculty, and we were trying to seat these people. Everybody's coming in at once. There is no time to interact, okay? So we had all of the course staff were the LCAs, local computation algorithms, and we had no time to interact with each other, but we had to direct students to seats in a way, and they were kind of coming at us randomly. And we had to direct them in a way where at the end there would be a pretty good maximal independent set. Okay, so that's why you can't always allow interactions. You may not have a way of talking to each other, but I need to be consistent with what the rest of the course staff was doing. So we had a plan before they came in and we executed, and it worked, just to let you know. Okay, so these are problems that could happen in general, not just when you're giving an exam in a course. And the question is, can we avoid these problems of the query order, remembering past choices, and allowing simultaneous non-interacting copies? Okay, so the difficulty is, as in maximal independent set, is there could be many legal outputs, and you have to agree on one. Okay, so here's the model that was suggested with Tamir, Vardy, and Shi, and also with Alon, Vardy, and Shi. We call it the local computation algorithms model. It's a sequential computation model, not a distributed model. So it's often called the central local model to distinguish it from the distributed local model. Okay, so here's the model. You have a huge input X. That's written down. And there is a very large output Y, which is not written down, but this is what we want to access. So we're going to assume there's this local computation algorithms processing unit, which gets queries. So it gets queries say I1. And when it gets query I1, it can make some probes into the input. Look, what's the value of the input at location J? What's the value of the input at location K? And so on. And then it figures it out and answers Y sub I1. So it gives you the value of Y at location I1. Then it gets another query for I2. Okay, makes some more probes and then answers Y sub I2. Okay, now you could have swarms of these LCAs, which are these, which initially share a short random string, but then they're independent, non-interacting copies. So there's no communication between them other than the initial share of the short random string. And they each get queries. The queries might be similar queries. It might be queries that interact with each other. It might be totally independent. But somehow they have to give the illusion of a fully constructed output. So they have to agree on the queries that if two LCAs were asked the same query, they have to agree, but they also need to be consistent with each other so that this could be completed to a fully constructed output. Okay. Now, the hope is these LCAs use sublinear time, space, and randomness, and in particular, can't remember their past decisions. So this is sort of the model. And one way to think of it is you've got this LCA, it's got this little short random string that it was given, and it agrees on. There are many possible outputs for this input. So Y1 through YK are all the possible outputs that you could answer for input X. The random string gets tossed that selects a specific output, and then all the queries are answered according to that specific output. Okay, so sorry, I went too fast there. All right, so that's the model. All right, how do we design good LCAs? It kind of might sound like magic, but it turns out that one major way of designing them is to use ideas from distributed algorithms, okay? And in particular, there's an idea of Parnas and Ron that shows that local distributed algorithms give really good LCAs. So what the insight is if there's a k-round distributed algorithm for maximal independent set, then, okay, first of all, I just want to say something. What is a k-round distributed algorithm? Just to remember, distributed algorithms, they compute on these local distributed algorithms. Their computation input is the network graph. Okay, so if I'm doing maximal independent set, my input is my communication graph. It's the same. Okay, so so that's one thing to notice. The other thing to notice is what can you do in a round? You can look at your random bits. You can look at your local memory. You can construct a message based on that, send messages to your neighbors, and you can receive messages from your neighbors, okay? So if there's a k-round distributed algorithm for maximal independent set, then V's output can depend only on inputs, say the unique IDs, the neighbors, and the randomness, and the computations of a k-radius ball around V, okay? So if you have a one-round distributed algorithm, I can look at my input, I can look at my randomness, I can use that to send a message to my neighbors. I will also receive a message from my neighbors that depends on their input, their randomness, but they have, when they construct their message to send to me, they haven't yet received anything from their neighbors. So at the first round, the messages I get can only depend on my neighbor's input. Okay. After 2 rounds, they can already have received messages from their neighbors. So after 2 rounds, I can depend on information that comes from 2 hops away. Okay. And in general, I can only depend on a k-radius ball around V. What's good about that? Well, that's a k-round local distributed algorithm can be simulated sequentially in the degree delta to the k probes. Okay, so if I'm a sequential algorithm, I can look at all the inputs and all the random bits and all the IDs of all the nodes in this k-radius ball, and I can figure out what V's view of the local distributed algorithm would be after reading these delta to the k locations. Okay, and once I do that, I can figure out V's output. So if there was a k-round distributed algorithm that told V whether to be in the independent set or not, then I can simulate it in delta to the k, time sequentially, and figure out whether V should have been in the independent set or not, according to that algorithm. Okay, so that's the idea here. It's an exponential increase because we're going from distributed time to sequential time, but it's still something that's helpful when k is small and delta is small. So the big question is, how big is k? All right, so before I continue and we talk about how big is k, I want to make a simplifying assumption for the talk, and that's about the randomness. I want to assume for this talk that everyone can access everyone else's randomness at every time step for free. So just assume there's this public randomness billboard and I give you free access to it. So, you can implement this often with pseudo-randomness, or you can distribute k-wise seeds for k-wise independent random bits. So there's a lot of ways you can implement this billboard, but for now, just assume it's out there completely for free and everybody can access it. Okay, so given that, just a reminder where we are trying to figure out our delta to the k local computation algorithm. How good or bad is this? And to figure that out, we need to know how big is k for the k-round distributed algorithms for maximal independent set. Okay, so first of all, don't get depressed, but lexicographically, first MIS is P complete, which means it's that particular problem is problematic for parallel and distributed computation. But luckily, it turns out you can, in order log n rounds, find a maximal independent set. You can do much better now. I'll say more about that in a minute. But just the classic algorithm up until a few years ago, this was a pretty good algorithm, would have led to a delta to the C order log n LCA. And the reason I'm mentioning this, what happens with this classic algorithm, is I just want to point out that log n rounds isn't really good enough for constructing LCAs. Okay, so that's super linear, and we're looking for sublinear time LCAs. So I just want to be clear that when we are talking about local algorithms, we actually need very local. We need sublogarithmic rounds. Okay, so the idea prime is to use distributed algorithms to what is now called shatter the graph. And here's an example of the Luby algorithm. You can initialize, this is a simplified version of Luby's algorithm. You can initialize all nodes to green, and each node marks itself red, meaning I volunteer to be in the independent set, with probability 1 over 2 times the degree. This should actually be delta. And for all volunteers, they check if their neighbors if any of their neighbors have volunteered. And if U is such that none of its neighbors volunteered, all of its neighbors are still green, then U is safe. It can go into the maximal independent set. And when it does that, it deletes itself and all of its neighbors from the graph. And what you can show is that this happens likely enough that something like with probably 1 over 4 delta. Okay, so that's great because it means that after you do this thing order delta times, then a large fraction of the graph is gone. All right. I just want to mention, remember our public randomness billboard assumption. Here, the random bits can be made pairwise independent. So a log n bit seed suffices to generate the bits for all of Luby's algorithm through all the rounds. Okay, so after you run order delta rounds of this distributed algorithm, you ran things. Where am I? Okay, then, okay, so you run order delta rounds of the distributed algorithm, and this guy put himself in the maximal independent set, this guy put himself, and you can run this, you can pick a constant that's large enough that say 99% or even 99.99% of the graph has already been decided either in or out of the maximal independent set. But the worry would be that maybe the undecided nodes are all in a big clump, and You just can't break that clump. The beauty is, though, is you can show that all the remaining live components are small. And when I say small, I mean logarithmic. And this is an analysis that's similar to Beck from the constructive version of the Luby's local lemma. And you can show that every one of these live components is logarithmic in size, and therefore you can solve the remaining live components via brute force. Okay, so we can go to each one of these and figure out, oh, this is a live component. I'll pick the lexicographically first independent set, and those guys I'll stick in the independent set. Okay, so that's how we'll stick in these purple guys, just in some sense they're lexicographically first. And this shattering idea was later used and greatly improved by others, and I'll say more about that later. Okay, so just one more view of this particular algorithm before I move on. In preprocessing, all the copies of the LCAs agree on some single log n bit random seed. That's so that we can generate all the pairwise independent bits and we can get all our randomness for free. So you can ignore this preprocessing because that's the part that I said we're just going to assume that we're rid of. But now we're just going to generate a subroutine called alive that tells us that after the Parnas-Ron simulation of V's local view of this Luby distributed algorithm, is node V still alive? Okay, so this is going to take delta to the number of rounds, which is order delta queries. So it's delta to the delta. If our degree is constant, that's not bad, but it is exponential in the degree. And this tells you if V is alive after a constant number of rounds. We'll pick some constant. So what does the LCA do? First of all, if V's output is determined by alive, great, output the value that was determined by alive. Otherwise, we're going to find V's small live connected component via BFS. I'm going to go to my neighbor, ask, is W alive? And then I'm going to go to W's neighbor and check which ones of those are alive. And we're going to find the whole connected component. And then once we find the whole connected component, we'll find the lexicographically first MIS of this live component, and then figure out, is V in that lexicographically first MIS? If so, output yes. Okay, so that's the whole thing. This is what it looks like. All right, so that's the main idea. I want to mention that there are other ways of constructing LCAs, not all. I don't know why that happened, but there are other ways of constructing LCAs via simulating greedy, for example. I'm not going to talk about that today, but I just wanted to say there's a whole line of work using that as well. Okay, now there. Okay. All right, so how fast can LCAs for maximal independent set be? Well, as far as dependence on n, the line of work I've described and further results have given results that are polylogarithmic in n. There is a work of Evan, Medina, and Ron based on a different distributed algorithm that gets log star of n. So this is the best I know so far. What about dependence on delta? Okay, so what I just showed you was exponential, and through a sequence of improvements up to this recent kind of newish, it's from 2019, of Ghaffari and Wito, this gives very close to polynomial in the degree dependence and in delta and polylogarithmic in n. And so the open question is, can you get polynomial in delta dependence for maximal independent set? Okay, so that's one open question. Lots of other problems have been considered in this model. Here's a completely non-exhaustive list, but maximum matching, vertex cover, all kinds of scheduling problems for radio broadcast, job scheduling, coloring of graphs and hypergraphs, set cover, logical problems such as KCNF, Luby's local lemma type problems, mechanism design, online algorithms, and load balancing of balls and bins are other examples of problems that have been considered in this model. In these examples are all polylogarithmic number of probes, sequential. And I just wanted, yeah, okay. Another set of LCAs have been constructed to find sparse subgraphs with connectivity properties, such as give you a graph G that may have lots of edges, but I want to find a small sparse subgraph of G which preserves the connectivity of G. So I just want to basically keep enough edges to preserve connectivity. That's been considered. I also may want to keep a subgraph that is a spanner of low stretch. That's also been considered. The query you might ask is edge UV, which is in the original graph, is it also in the sparsified subgraph? Okay, so there have been works on this, and these latter two have looked at high degree input graphs as well. Okay, so, but all I want to say is what's desperately needed is more techniques for handling large degrees. Okay, so I want to turn to a different kind of problem, and that's that of generating random colorings of large graphs. So now you have a large graph. The input is just the graph, and what you want to generate is a random coloring, not just an arbitrary coloring. Okay, so your input is a graph G. We're going to assume again a maximum degree delta. I'm going to give you more colors than delta, so I know it's possible to get a coloring of this graph. In fact, here we're going to give you 12 times delta many colors. And what we'd like to output is a uniformly random but valid coloring of G, and I'd like to get local access to it. So the type of query we'd like to support is, what is the color of node V? And we'd like to do this with sublinear probes to G, if possible. Okay, so how might we do this? Well, let's look at what's done sequentially, and let's think of the basic sequential Markov chain, where the number of colors is at least twice the max degree, and this is due to Friese and Vigoda. What they say to do is pick a random, everybody starts with an arbitrary coloring, but now I want a random coloring, not an arbitrary coloring. So what we're going to do is random node V. I'm going to pick a random node V, and V is going to pick a random color. And then we're going to update V to this new color if it doesn't conflict with its neighbors. We're going to do this lots of times, n log n times. At this point, because of coupon collectors, we've hit all the nodes V. We've recolored each one of them at least once, more like log n times. And what they showed is that this actually does give this actually gives a random coloring. Okay, that's the sequential case. All right, now we want to figure out how to answer queries of the form, what's the color of node V at time t? And in order to answer such a query, we're going to have to figure out when was V last picked, which color did it choose, did it conflict with its neighbors? And to figure that out, I have to look at all the neighbors of V. What was their color at that time? When did they last pick their color? What color did they choose? And did they conflict with their neighbors? And it goes on. And you can imagine this thing might be, if I follow back through in history, what I have to look at in order to figure out the color of node V at time t, it could get to delta to the t. Maybe we can say something like delta to the log n, because we're always picking a random node, and there's only n nodes, and we're only doing n log n steps. So each node only colors itself something like log n times. So maybe if I had a way of quickly finding when all the times I was colored, I could go back through that list and figure out something. So maybe I can only branch out by delta to the log n, but that's still omega n. So what do I do here? So again, we are going to use distributed computation. So we're going to look at the distributed Markov chain results of Feng Sun Yin and Fisher Ghaffari and Feng Hazen Yin. Here, n nodes simultaneously choose random colors as proposals, and they do something like what the previous sequential Markov chain did. They update their color if there's no conflict with any neighbor's current color or the new proposal. But they also check from the point of view of the neighbors that no neighbor proposal conflicts with their current color. Okay, so they check all these, they're very careful. They check all these things, and if all these are satisfied, then they can update the color. Okay, so this is a distributed algorithm for randomized coloring, and we'd like to see, can we use this? The problem is this needs log n rounds, and as we saw before, if you have a log n round algorithm and you use the Parnas-Ron reduction, you get delta to the order log n, and that can be superlinear. Okay, so that's not going to be enough. But the insight is, so let's see what we're going to do. We're going to give a subpolynomial time algorithm. It's going to be n to the alpha for alpha less than 1. And this alpha is going to get smaller with more colors. So as Q increases, the alpha can get smaller. And the type of question we're going to ask is accepted V, C, and T. Does V accept proposal of color C at round T? Okay, so I'm not asking what is the color of V at time T. I'm asking does V accept the proposal of color C at round T? And you'll see that this is a weaker question, and that's going to help us make progress. Okay, so the first attempt would be for each neighbor, the first attempt at implementing accepted to figure out whether V accepts the proposal of color C at round T is to do what we did before. For each neighbor, decrement the time until you find the last accepted proposal. That tells you what the neighbor's color is, and you're done, except that this takes forever to simulate sequentially. Okay, so the actual thing we're going to do, the insight here is you just need to make sure that the neighbor isn't colored with color C. You don't have to know the neighbor's color. You just need to know that it's not C. Okay, and this is where we're going to get a savings. All right, so for each neighbor, we're going to jump back to the previous time the color C was proposed for that neighbor. Then we're going to increment forward to see if it's overwritten. Most of the time, it gets overwritten pretty quickly. Okay, so most of those leads, we don't actually have to follow very far. And just a few of them will we have to really check out and investigate. And so our sequential running time is not going to be that bad. Okay, so that's the insight here. And that gives us an n to the alpha, which is it's polynomial, but it's n to the alpha for alpha less than 1 running time for LCAs for random coloring. Okay, it's open to see if one can do this in polylogarithmic time. It's also open if you can use fewer colors. We were quite liberal with colors. Can you get down to the 2 delta that was needed in the sequential case? Perhaps you can. So I think so the open problem here is either improve the time, improve the number of colors, or both. Okay, so I want to move now to, I know I call this a survey on local algorithms, but I'm about to switch models on you. I want to talk about generating large random objects. And what we saw in this coloring is you may not want to generate them up front. You may want to generate them locally on the fly. But just a warning again, this is a different model because now we get random bits. There's a local generation algorithm. The user will query what is the value of the random object at this certain place. It'll get a response. And the local generation algorithm has a lot of space. It can partially generate this large random object. And every time it gets a query, it may need more and more space. Okay, I just want to stress that the coloring algorithm was in the local computation model. It did not need to store space in between queries, but I am now moving to a different model where you do have the ability to keep around information about your past answers to queries. Okay, so this is, so we are allowing long-term memory. This is not appropriate for independent, simultaneous, and consistent agents, but you still do want sublinear probe complexity. All right, so again, we want to answer in sublinear time. We'd like consistency over the queries, but we can store past decisions. And what we want here is distribution equivalence. We'd like our output distribution to be epsilon closed and L1 distance to the goal distribution. So let's take a really, really simple problem of a large 1D random walk. Okay, so you go up with probability a half and down with probability a half. So think about walking on the line. You go left or right with probability a half. All right, so now I want to ask at time t, what's the position of the walk at time t? Okay, and I may get some response that says, you know, I'm plus 10. And then I may ask about this time over here. Here I was minus 3. And at this time I might be plus 2. So I make these arbitrary queries at different times, and I'd like to answer where this walk is. All right, so I'd like to be able to answer those queries in a way that's consistent with a uniformly random walk. but I don't want to have to compute the whole walk in advance. And it turns out that this is just, this can be done via local generation of the hypergeometric distribution based on techniques from Gilbert et al. And Goldreich et al. And you can answer such queries very quickly in logarithmic time. Okay, so this is a very simple case. I want to make it a little harder. What about random Catalan objects? So these are objects such as random walks on the line that have to stay non-negative. And these would describe random parentheses, such as random well-bracketed expressions, or they're often called random dyke paths or random rooted trees is another way to explain them. Okay, so this is what they look like. And what they pertain to is that at this point you have from here to here, you've closed off one set of parentheses. Here you have a left parentheses, a right parentheses, and you came back to 0. Here you might have left, left, right, right, and you came back to 0. So this is sort of what this looks like. This is left, left, right, but then another left, and then another left, and then a right. And so it's going up every time you have a left and coming down every time you have a right. Okay. All right, so that's the type of random walk we're looking. So what we'd like is a random well-bracketed expression. And the types of queries we'd like to ask, as before, we'd like to ask how far along, as before we asked, what's your position on the line after t steps? Here we may ask, how far up the nesting are you? Okay, so what is your height? Or actually, I guess we called it depth, the bracket nesting depth query. And the other thing you might want to know is, where is your matching bracket? If this is my left parentheses, I want to know that this is the right parentheses that matches me. Okay, so matching bracket queries. All right, well, one issue with this is, how are we going to do this? The hope is that once you generate height query answers, that what happens in between let's say I've queried a place here and I've queried a place here. What happens in between? The hope is it's somehow independent from another region that was unqueried in another part of the bracketing. So that would be a good hope. The challenge is the fact that any prefix has a non-negative sum can add some constraints to the generation process here. So it turns out you can do this. You can write out some sort of complicated CDF, which generates the height of a midpoint of some unqueried interval. And then you can recursively divide the relevant interval in half. And you can keep doing this until you get to the part that was actually queried by the user. So it all depends on coming up with these CDF. The problem is it's kind of complicated, so I'm going to say a little bit about what to do about that in a second. In the first return queries, again, things get complicated because of this non-negative sum issue. So I just want to, I don't want to try to explain what the solution is here because I don't have the time, but I do want to say you can keep information as to the lower bound on each interval and make sure that this information is always, this lower bound is always achieved at the boundary. And so what you'll do is you'll just, the user makes certain queries, but I'll make new queries as the algorithm to keep these intervals where I know where the walk was at those points of the interval. Okay, and I'll ask enough queries so that I always have the lower bound at the boundary. And I'll just keep this invariant. And when I need to break up, like if I have a query to the middle of some interval, I will generate a lower bound for that interval and break this whole interval up into subintervals in order to satisfy the invariant. And I'll keep doing that until I reach the queried point. Okay, so the difficulty here is going to be computing the CDF. It's sort of a complicated expression, and we have to do this by approximating the CDF and using rejection sampling in order to do it. So I'm not going to say more about this now, but what I do want to say is, what about random walks, not just on lines and random walks that don't go negative? What about random walks on graphs? So this is a newer work. Here you're given a graph G and a start for a text S, and you're asked what's the location of the random walk at time t. Now t can be polynomial in the number of nodes in the graph. It can be square root the number of nodes in the graph. It can be whatever you want, but we'll see which parameters actually make sense for what we're able to do. Okay, so for certain structured type of graphs, you can answer such questions quite quickly, even polylogarithmic time for the hypercube, the cycle, Cayley graphs, structured graphs such as tensor and Cartesian products. And in fact, you can do, okay, so those are polylogarithmic time. For general graphs, we don't have a solution, but if you do know the spectral expansion to be gamma, and this doesn't have to be a constant, it can just be any, as long as you know the spectral expansion, you can get a bound in terms of the spectral expansion, 1 minus 1 over lambda times square root n. Okay, and this is actually tight because for random graphs which have constant spectral expansion, you need root n. So root n is kind of the right thing for expanders, and if you have like weaker spectral expansion, you can get a bound in terms of that as well. All right, I want to say a little bit about this upper bound if I have time. Maybe not so much time, but I will say a little bit anyway. Okay, so given a query, because given a query to time j. Okay, so I have some random walk, and so far my my user has asked, where's the random walk at time 1? Where's the random walk at time t? Where's the random walk at time 10 to the 6th? Where's the random walk at time I, time 10, time k? And now I'm asking, the user is asking about time j. Where is the walk at time j? Okay, so let's let I and k be the times that are adjacent. Okay, and these are revealed either because they were queried by the user or because the algorithm already figured them out. Okay, so I'm saying this this xj is sort of in this area between xi and xk where nothing has been revealed yet. Okay, so let's kind of, so now we have it. So we're just going to focus on the part between xi and xk where nothing's been revealed. We want to know where are we at time j. All right, so there's some cases. If j is far enough from both I and k, then we're just going to pick it randomly. What do I mean by far? I need enough time to mix. Okay, so as long as I've had enough time to mix from both I and k, so we're just assuming that the backwards walk and the forwards walk is the same, or that at least I can calculate the backwards walk, is all I need to assume. And as long as we're far enough, we're just going to pick xj from the stationary distribution. Okay, so another case that's fairly straightforward to use is what happens if j is close to one of them, let's either xi or either time I or time k, and far from the other one, far enough that it has time to mix from the other one. Okay, so if xj is say close, if j is close to I and far from k, and it can be far more than 1 minus 1 over lambda times square root n. It could be n to the 1.5 far, n to the 10th far from xk. All right, so in that case, close is logarithmic in n, and far can be anything. What we're going to do is the one we're close to, say it's xi, we're just going to start taking a random walk from xi until we reach time j, and those nodes will be revealed. Okay, so those are now set in stone. Xi went to xi plus 1 to xi plus 2. We just picked those, we flipped those coins, and we know where this random walk went. So these are our new revealed nodes. Okay, and we're going to set, once we get to time j, that will be our output for xj. Okay, so those were the two easy cases. A little more complicated is what happens if we're asking about a place that's both close to I and k. Now we have to find a random path between xi and xk. And in that random path, we need to output xj. So that's the goal. Now, how do we find a random path that starts at xi? It's easy to find a random path that starts at xi. It's easy to find a random path that ends at xk. What's not so simple is how to find a random path that starts at xi and ends at xk. So we're going to take random walks from xi. And so first attempt would be take random walks from xi until you find one that hits xk at time k. Okay, and then you would output xj. But that might take omega n time because most random walks from xi don't hit xk at time k. So it would take time until you find one of those, and you need to find a random such path. You can't just find like the shortest path or some arbitrary directed path. Okay. So attempt number 2, and this is the one that works, is this is a technique that's been used in several places. We're going to take walks starting from xi and more walks that end at xk until we find a midpoint collision. Okay, so we took some path from xi, and then there were a bunch of paths from xk that we took, but one of them collided with a path from xk. Okay, and so we're going to paste together these colliding walks. This gives you a uniformly generated path between xi and xk, but it's only going to take us square root n attempts to find such paths. These paths will be length logarithmic because j is close to I and k. So I and k in particular are close to each other in time. So these are short paths. But the number of prefixes and suffixes we need to generate to find a collision is something like root n. Okay, and once we pick this path, we look for time j, and we output xj. Okay, so that's what we do there. So I just wanted, I think I don't have much time left, so I'm just going to say one more topic that you might want to generate is what happens when you want to generate large random graphs. So it may be an adjacency matrix, it may be an adjacency list setting, and the question is, can you generate these on the fly? And it seems like an adjacency matrix, you can just flip bits as much as you want, but what if you have requirements, like you want it to be symmetric or deregular, or you want to support next neighbor queries? Is there a question?
No.
Okay. All right. So one challenge is how to handle dependencies. So the sources of dependencies could come from the model, what type of random graph you're trying to output, but it also could come from the type of queries you're trying to answer. So I want to just say there have been models that have been studied. There's a notion of huge random graphs and objects suggested by Goldrake, Goldwasser, and Nussbaum. In their notion, huge is exponential size, and the user does not query more than a polynomial number of locations. So in their model, it might be sufficient to generate a graph that looks random to a polynomial time algorithm. The model suggested, this was started by Evan, Levy, Medina, and Roseanne, and continued by Biswas, myself, and Anakia Pignani, is to look at large random graphs and objects, where large is polynomial size. You might eventually write down the whole graph, but you don't want to pay the cost up front. And your end result should be random statistically according to the claimed process. Okay, so the types of queries you might look at is UV an edge? What are all the neighbors of U? What's the next neighbor of U if you're doing it and following an adjacency list of U? What's a random neighbor of U? And you could look at all kinds of families, such as small degree regular graphs, preferential attachment by Evan, Levy, Medina, and Roseanne. Even Erdős and Renyi can get interesting when P is small. P is something like, say, 1 over square root n or 1 over poly log n, and you want to answer things like next neighbors or random neighbors. The stochastic block model, Kleinberg's small world model, and all of these have been considered. So I'm going to stop now with open questions. The open questions on this part of the talk is, of course, to generate other types of huge random objects, and whether the model in this second part of the talk actually needs to be weaker. Is there some way to avoid the need for long-term memory of past decisions? So that's those questions. In this talk, we talked about locality and distributed computing and local computation algorithms and their interaction. We talked about generating random objects. This notion of locality is also used in sublinear time approximations, partitioning of graphs and PageRank, massively parallel computation. There are lots and lots of open questions. I've mentioned many in the talk. I think one of the interesting ones is what is the role of sparsification and what other techniques can we develop for sparsification? And finally, what I wanted to give, I want to give a commercial for the workshop on local algorithms, WOLA 2021. It's going to be held this Monday and Tuesday, like in a couple of days, June 14th and June 15th, from 11 to 4 p.m. Now, 11, that's Eastern time. So 11 is whatever time it is for you right now. That is 11 a.m. Okay, so that's your time. And then it's going to last, it's going to be Monday and Tuesday for 5 hours. We have wonderful speakers. There are going to be different sessions, an Ask Me Anything, a poster session, junior, senior lunches, an open problem session. And for more information, of course, it's virtual, and of course, it's free. So please come. It's great. There's lots of cool new ideas all the time. So I think it's going to be great. So I think that's all I have to say. Thank you.
Thank you very much. So if there are any questions, please put them in the chat. But great presentation. So I can start with the first question. So you're talking that this is kind of the roots, or I don't know whether the roots, but at the beginning were very close related to distributed computing. Is there any way of formalizing something that if, for example, something can be done in local, can also be done in LCA, or as a lower bound, if something cannot be done in local, you are getting also some lower bound for, or local or any other model?
So you mean, when you say local, you mean distributed?
Yeah, distributed local model.
So the thing is, you can formalize, but when you go in a circle, you lose.
I see.
So anything you can do in the local distributed model, because of the Parnas-Ron reduction, you can do in the degree delta to the number of rounds.
Okay.
So it's exponential.
Okay.
Of course, anything you can do in the LCA model, if you can do it in the sequential log n time, you can also do it in parallel log n time or distributed log n time. But you lose when you go in a circle because of the exponential blow up. And then the hope is that somehow you can sparsify or not follow the local algorithm to the completion. Just use it to somehow simplify your problem and then do something else.
Okay.
But that's, really beyond Parnas-Ron, I don't know that we have anything that's like a flat out reduction, if this, then this. But we do have techniques.
Yeah, no, I understand. So there is a question from Ami Pass. Are there known connections between LCA and the evasiveness conjecture?
Oh, that's an interesting question. I don't know of any, but that's really interesting. I'm wondering if there's something known between property testing and evasiveness. Because I think that in the Goldreich-Goldwasser-Ron a paper, they mentioned evasiveness somewhere, but I don't remember what their results were, if any. But I don't know anything, not with LCAs, but it's interesting.
Okay, thanks. So in your talk, in your presentation, I don't know, in the first 15 minutes or so, you had some result for, I think, matching or MIS, I don't remember. You were saying that there is an upper bound of log star. And then when there is a dependency on delta, you were saying that this is essentially delta to log delta times log n. Did I read it right? So this is weaker than log star.
Okay. So there's, I see what you're saying. So the dependencies, I think that the results that get good dependency on delta have polylogarithmic dependence on n.
Okay.
So I don't know. Okay, so this actually is an interesting question. Can you get sub-exponential dependency on delta and get log star dependence on n?
Okay. Well, because the result as it was stated look weaker than the result log star.
Well, so I think those were thinking of, I see what you're saying.
Log star was with constant delta.
Yeah, log star was with
constant delta. Oh, I see. Okay, good.
Yeah, no, it was exponential in delta.
Okay.
Actually, I think we have one of the, I think maybe Guy Evan is on here, so he can tell us. But at least I saw him before.
Oh, he
So it's
must.
Evan, Medina, and Ron. So
Mhm.
if one of those people is here.
He's still here. At
Yeah.
least his name is.
Guy.
So, but I think it's time to finish. So thank you very much, Ronitt, for
Thank
the
you.
presentation.
Thank
So you know the drill right now. So I will end the session, and then if any of you is interested to join us in the table, including Ronitt, we hope that Ronitt will go to some of the tables. You're welcome to do so. There are always few people staying, so I hope to see you there in a few minutes.